Hello! So today I'm going to be doing some conservation problems. So we're just going to be looking at conservation problems as it relates to fluid flow through a pipe. We're also going to do a siphon problem and then finish up with a Pitot Tube problem. So let me just go ahead and pull up the problem that we're going to work through first, involving the flow of ethylene through a pipeline. So that's this problem number 4. So we're given a mass flow rate. That's 20 pounds per second of ethylene gas, and we can assume that it behaves ideally. And then we're given a temperature, an internal pipe diameter, and upstream and downstream pressure. And then we're interested in finding out the inlet and outlet velocities. And we also just wanted an explanation as to why the pressure falls. So this is my schematic drawing of that problem. So it's ethylene gas flowing through this pipeline. Ethylene, the chemical formula is C2H4, and that has a molecular weight of 28 grams per mole. And then I converted all the other imperial units that we were given into SI. So that's all this stuff right here. So we're just going to use a mass conservation relationship. We're given the mass flow rate, 9.072 kilograms per second. And we know that that's going to equal to the density times the cross-sectional area times the velocity. And we know that mass is always conserved, so the inlet density, cross-sectional area, and velocity is going to equal the outlet density, cross-sectional area, and velocity. So in our case, the cross-sectional area is constant, so A1 is equal to A2. So we know that we just have a relationship where the inlet density times the inlet velocity is equal to the outlet density times the outlet velocity. So we're going to use that relationship, but first off, we just want to use the ideal gas law to determine the density at the inlet and at the outlet. So with the ideal gas law, we can determine this relationship right here. So that rho is equal to the molecular weight multiplied by the pressure over the universal gas constant times the temperature. So that rho1 is equal to, I'm going to do it in kilograms, so 28 kilograms per 1,000 moles. And then the pressure 1, that's an 8, sorry. Pressure 1 is 4.137 times 10 to the 5 pascals, and we're dividing that by 8.314 joules per mole Kelvin, and the temperature in Kelvin we need to add 273.15, so we get 288.71 Kelvin. Okay, and if you crunch that number, you're going to get a density of 4.83 kilograms per meter cubed. So joule, you can break that down into, I think it's kilograms meter squared per second squared, and then that would cancel out everything if you also convert the pascals, which I think is kilograms per meter second squared, I think. But all the units will collapse down to kilograms per meter cubed. So we do the same calculation for the second density, and the only thing that's going to change is our pressure. So you do the exact same calculation, and you end up with 2.01 kilograms per meter cubed. Okay, so now that we have both the density at the inlet and the outlet, we can focus our attention on getting just one of either the inlet or the outlet velocity. I'll go ahead and start with the inlet velocity. So we're just going to use that relationship that m is equal to rho AU. So m dot, mass flow rate, is equal to density 1, cross-sectional area 1, and U1. So I'm just going to solve that for U1. So U1 is equal to m dot over rho 1a, and the cross-sectional area is pi d squared over 4. So if I plug that in, I'm going to get 4 m dot over rho 1 pi d squared. So let's go ahead and plug that in. So we get 4 times 9.072 kilograms per second, and we're dividing by density of, let me go ahead and, so 4.83 kilograms per meter cubed pi, and our diameter squared, which is 0.2032 meters squared, and that will give us an answer of pretty much 58 meters per second. It's 57.97 meters per second. Okay, and then we can just do the exact same calculation, or we could manipulate this relationship to get the outlet velocity. So I'm just going to manipulate this relationship. So just imagine that we have A1 canceling with A2, and then I'm solving for U2, so that U2 is equal to rho 1 U1 over rho 2. So that's pretty easy. You can just plug and chug that, and you should get an answer of 139.1 meters per second. So that is the first problem. The second problem that we're going to look at is a siphon problem. It's a little bit more complex, but not much more. Okay, so here is our siphon. So we're given the cross-sectional area of the pipe, and that would just be like right here, the cross-sectional area. And then we're also given the total length of pipe, which is 5.5 meters, and we know that the fluid is water, and it's discharging at the bottom here. And let's see, and we're neglecting pipe friction. There's no work going on, and we're interested in determining the outlet velocity, the discharge velocity, and then we also want to know what the lowest pressure is in bar gauge pressure throughout the system. So let's go ahead and get started on that. Just 1 second while I copy and paste my schematic. Okay, and the first thing that I usually like to do is just make sure that I understand the drawing, and that I label points accordingly. So we're interested in the discharge velocity, so I'm going to just call this point 1, and I'm going to call this point 2. And then we're also told that we want to figure out where the lowest pressure is. Intuitively, we know that things flow from areas of high pressure to low pressure. So if the water is flowing up this, we know that the pressure has got to be lowest up top. So I'm going to call that point 3, but we can also prove that mathematically. Okay, so this is a momentum conservation problem, or I guess just an energy conservation problem. So we're going to be dealing with potential energy, kinetic energy. There's no work, there's no friction. Also going to be dealing with kinetic energy. So let me just go ahead and copy and paste general Bernoulli's equation over here. So this is the equation that we're going to be using to do this problem. And the first thing that we're going to want to do is just simplify it. So we know that there's no work. Cross that out, no friction. So we know that U2 is going to be much less than U1. So we could, for practical purposes, we can just neglect this term. It's functionally going to be 0. Okay, and then we know this from our schematic drawing is just going to be Z2 minus Z1 is just going to be 1 meter. We know that P2 is equal to P1, which is just equal to the atmospheric pressure. So this term is going to go away. And then we're interested in just what U1 is. So we just need to do a little bit of algebra. I'm just going to do it in my head. So we have U1 is equal to 2 G so we're going to get this relationship. So if we just go ahead and plug in the numbers, we have 2 times 9.81 meters per second squared, and we're going to multiply that by 1 meter and take the square root. So let's make sure our units make sense. We're going for velocity, and we're taking the square root of meters squared per second squared, so we'll end up with meters per second, so that's good. And we're going to get an answer of 4.43 meters per second. Alright, so now we want to figure out where, I guess we already kind of intuitively figured out where in the system the lowest pressure is going to be, but let's go ahead and just show it mathematically. So we have, let's compare 0.1 and 0.2. And we're just going to use the Bernoulli equation again. So if we're comparing 0.1 and 0.2, what can we cancel out? So we can cancel out the velocity, because we know that the velocity is going to be constant throughout that system. Just pretend that this is U3, not U2. So we were given the elevation, so Z3 minus Z1 is going to equal to 2.5 meters. And then we're trying to determine where the pressure is lowest. We know P1 is going to be P atmospheric, so we're trying to determine what P2 is. Okay, yeah, so let's just go ahead and get started. We cross out work and the friction force. So if we solve for P3, that is going to equal to rho G change in Z plus P1. This is going to be negative. Sorry. Yeah, that's going to be negative. And we also know that the change in height, so Z3 minus Z1 is a positive quantity, so that means that whatever our atmospheric pressure is, we're going to be subtracting something positive, so we know that P3 must be P1. And we also know that as height increases, it's going to be getting more and more negative, this entire term. So that could be an explanation as to why the pressure is higher at the top than it is, say, right here. And this relationship may look familiar from the manometer problems. So if we were doing a manometer problem and we were interested in the pressure at point 1, we would just say that the pressure at point 1 is equal to the pressure at point 3 plus just rho G and then whatever the change in height is. So you can see that this is the exact same expression, just swap the P1 and P3 around. So that will do it for the siphon problem. Once again, pretty easy. And I'm going to finish up with a Pitot Tube problem. Okay, so just came back from a short break. Going to explain what a Pitot Tube is. So on the left here, this picture on the left, we have a Pitot Tube in a stationary position, so this is just stationary. And then the Pitot Tube on the right is in motion. So pitot tubes are maybe used on a boat, let's say. So if you imagine that this is the bottom surface of the boat, and then there's just a little tube that sticks down, and then the pitot tube is used to determine the velocity of the boat. When it's stationary, there is no height of the fluid, and then when the boat starts moving, you can see that the fluid rises in the pitot tube, and then that height will allow you to determine the velocity. So you can just draw streamlines. Imagine this is in motion. Okay, so let's go ahead and just do a pitot tube problem, or at least symbolically, let's do a pitot tube problem. And that way we can determine the velocity given the height of the fluid, or given some pressure measured with pressure transducer, which is probably the more realistic way. You would measure the pressure difference with a pressure transducer, and then use that information to calculate the velocity. So let's go ahead and just call this point 1, and let's call this point 2 up here. And then let me go ahead and copy and paste the Bernoulli equation back over. So just 1 second here. Okay. So with the Bernoulli equation, let's just start canceling things out. It's usually the right idea. You just want to figure out what you can cancel, so we can cancel out work and friction where there's no work going on, no pumps or turbines, anything like that. Friction, I mean, technically there would be some frictional effects, but we're just dealing over such a short distance that all the frictional effects are going to be negligible. So we know that we're going to be moving, so there is going to be a velocity at point 1, but in point 2 there's not really going to be any velocity, so we can cross that out. Symbolically, we know what Z2 is and what Z1 is, so this will be our delta Z, and delta Z is going to equal to H plus capital H, lowercase plus capital H. We know, and we can determine an expression for P1, and we know that P2 is just going to be the atmospheric pressure. So let's go ahead and do that. Just 1 second. Okay, so P1, and this is just like the manometer problems, we just want P1. So that's going to be P2, which is atmospheric pressure, plus the density of the fluid, times the gravitational constant, and times the height. So it is going to be the capital H, because it's only this distance to the atmospheric pressure. It might seem intuitive that you would want to go to H plus lowercase h, but really we just want the height until you get to the surface. So we just want the capital H height. So that's going to be what our pressure 1 is, and then we're just going to start plugging stuff in. So we have that U1 squared. I'm going to do some algebra right now. So we're going to get a, let's see, P2 minus, and then I'm going to plug P1 in, which is P2 minus rho GH. That's going to be over rho. And then we're also going to be subtracting from that G times H plus lowercase h. Okay, and then we're going to multiply this entire quantity by 2. Okay, and we can see that the atmospheric pressure cancels out. We can see that this term right here and this term are going to cancel out. So what we're going to end up with is an expression saying that U1 is equal to the square root of 2 gravitational constant times the height of the fluid above the surface. So 2g lowercase h. So that's going to be one type of the problem. Now, I mentioned earlier that in a more realistic situation, you're going to be given the pressure measured with a pressure transducer, which is just going to be gauge pressure. So if we're doing a problem like that, then just a little bit of manipulation. So we're no longer going to call this point 2. That is going to, we're going to change what we call point 2. We're going to call this right here point 2. And that's still just height. Goes from the surface. Sorry, just let me fix up the sloppiness. Okay, so let's go ahead and do the problem if that is the case. So again, we're going to be using the Bernoulli equation, and we are going to cancel out the exact same things. And what we're going to end up with, so let's say, if you're measuring with a pressure transducer, what you're going to get is an expression that says P. It's going to say like P2 minus PATM, so it's going to be gauge, is equal to, so let's just look at this picture. So normally if we were doing a manometer problem, we would say that P2 is equal to the pressure right here, which is atmospheric pressure, plus rho g lowercase h. So I subtracted the atmospheric pressure over, so we know that this is going to be rho g lowercase h. So we have that information on hand. And then when P1 is going to be the same thing. P1 again is going to equal to our atmospheric pressure, so PATM, plus rho g capital H. Okay, and then we're still solving for U1, so we can say that U1 squared is equal to 2 times the quantity of P2. So let's just say P2 minus the atmospheric pressure minus rho g capital H, and that's all going to be divided by the fluid density. And then we're going to subtract off g times capital H plus lowercase h. So this term will cancel with this term. Made a mistake somewhere, just 1 second. Okay, yeah, so our change in height is not h, capital H plus h, it's just the capital H. Because we're just going from here to here. So our point 2 is not up here anymore, it's just right here. So let me just go ahead and erase that lowercase h. That didn't really work out very well. 1 second. Okay, and now these terms will cancel out. And what we're left with is an expression saying, U1 is equal to the square root of 2 times P2 minus PATM over rho. And you can actually see that this is exactly the same expression as this. If we plug in this identity right here, that P2 minus PATM is equal to rho GH, plug that in there, the rho's will cancel out, and then what you'll be left with is the square root of 2GH. Yeah, so that's pretty much all there is to a Pitot Tube problem. Once again, pretty simple. We're just building up complexity. We'll get to a little bit harder applications of energy balances. So until next time, I'll see you later.